Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a fascinating paper called Absolute Zero, Reinforced Self-Play Reasoning with Zero Data. It's a real head turner, I think.
Definitely. Zero data, that's a bold claim right from the start. I mean, in the world of deep learning where we're constantly chasing bigger data sets, it's almost rebellious.
Rebellious or maybe just realistic? I've always been a bit skeptical of the more data is always better mantra. Seems like we might be missing something fundamental if we're just throwing data at the problem.
I'm with Sarah on this. It feels a bit like brute forcing the problem. This whole idea of self-play with zero data, it's intriguing. The question in my mind is, does it actually lead to genuine understanding, or is it just clever trickery?
Well, that's exactly what we're here to unpack. For those who haven't had a chance to read the paper, the basic idea is that they've created an AI agent that learns to solve problems through self-play without being trained on any external data. It essentially learns from scratch by interacting with a simulated environment.
Yeah, and it's not just some simple game they're tackling. We're talking about complex reasoning tasks. It reminds me a bit of AlphaZero, which mastered Go and chess using self-play, but this absolute zero approach seems to be pushing the boundaries even further, tackling problems that require more abstract reasoning.
See, AlphaZero, to me, while impressive, is still fundamentally a pattern matching machine. It's incredibly good at it, but it's not actually understanding the game in the way a human does. I'm curious to see if this Absolute Zero goes beyond that.
That's a good point. It makes you wonder about the level of abstraction the agent is actually achieving. Is it really developing a high-level understanding of the problem, or is it just discovering clever sequences of actions that lead to a solution? I mean, can it generalize to slightly different scenarios, or is it only good at solving the exact problem it was trained on?
That question of generalization is key. One of the things that excites me most about this research is that it might offer a path to building more robust and adaptable agents. Current AI often struggles when faced with situations it hasn't seen before, but this approach seems to encourage the development of more flexible strategies, like a human who can figure out new ways of doing things without tons of examples.
Absolutely. The potential for generalization is huge, and the fact that they're achieving this with zero data is mind-blowing. It suggests that the algorithm itself is the critical factor, not just the sheer volume of information. This could really change how we approach AGI. Imagine, instead of needing massive datasets, we focus on designing smarter, more efficient learning algorithms that can bootstrap themselves into intelligence.
I'm still not entirely convinced that deep learning, even with clever self-play tricks, is the only way to get there. I think we need to consider neuro-symbolic approaches where we combine the pattern recognition capabilities of neural networks with the reasoning and knowledge representation of symbolic AI. That's where true understanding, and therefore generalization, will come from, I think.
I agree that there's probably a limit to what you can achieve with pure pattern matching. I keep thinking about how humans understand spatial relationships. We don't just memorize a bunch of images, we develop a mental model of the world that allows us to reason about objects and their positions. Even when we've never seen them before, we effortlessly translate between different coordinate systems, from the coordinates on a map to the visual coordinates in our eyes. And I don't see how deep learning can easily achieve that.
That's a fascinating point, Donald. Thinking about coordinate systems, I was reading about how the brain uses grid cells and place cells to create a spatial map of the environment. Could we incorporate similar mechanisms into AI to give it a more robust understanding of space and time?
Interesting. But I think DeepMind is already exploring things like that, right? Building architectures that mimic aspects of the hippocampus. The beauty of deep learning is that it can, in principle, learn these representations automatically, without us having to hand engineer them. The Absolute Zero paper is basically saying that with the right algorithms and enough self-play, it can discover these efficient representations on its own.
But how do we know what it's actually learning? That's the problem with these black box models. We can see that it's solving the problem, but we don't really understand why. And if we don't understand why, how can we be sure that it's not just exploiting some superficial correlation in the environment?
Exactly. It's like teaching a dog to do a trick. The dog can perform the trick perfectly, but it doesn't actually understand the underlying physics or mechanics. It's just learned a sequence of actions that lead to a reward. And that reward, whatever form it takes in this paper, might be obscuring the true nature of understanding.
Right. That reward-based learning in the paper, it sort of reminds me of the reward-based learning mechanisms in the brain. But can we build a metric to assess whether these computational models which are purely algorithmic, can also exhibit a sense of purpose? Or is it just reinforcement signals? It's a tough question, and I think it gets to the heart of what we mean by intelligence.
I think purpose is too strong of a word. It's more about optimization. The agent is trying to optimize its behavior to achieve a certain goal, whether that's winning a game or solving a puzzle. And as it gets better at it, it develops more sophisticated strategies and representations.
But isn't that just sophisticated pattern matching? It's optimizing for a specific reward function within a specific environment. Change the environment or the reward function, and the whole thing falls apart. True intelligence, I think, is about being able to adapt to new situations, to learn new concepts, and to reason about the world in a flexible and general way.
And that adaptability, I think, is fundamentally linked to the ability to translate between different representations. Imagine you're trying to navigate a city. You might use a map, GPS coordinates, street signs, or even just your own intuition. A truly intelligent agent should be able to seamlessly integrate all of these different sources of information and use them to plan a route.
Yes, and that brings me to another point I was considering, the concept of zero data and its connection to embodied cognition. I wonder if an agent learning through self-play develops an internal representation of the world that mirrors the sensory experiences of a physical being, and if that can be measured.
That's an interesting idea. But I think the beauty of this approach is that it doesn't need to be embodied. It can learn abstract concepts and solve problems without having any physical experience. The agent is learning purely through simulation, which makes it much more scalable and efficient.
But isn't embodiment crucial for grounding intelligence in the real world? Without sensory experience, how can an agent truly understand concepts like gravity or friction or pain? These are things that we learn through interacting with our environment.
And I think that interaction is also key for developing a robust understanding of space and time. We don't just passively observe the world. We actively explore it, manipulating objects, moving around, and experiencing the consequences of our actions. And that experience, I think, is essential for building a truly intelligent system.
It does seem that the human brain's ability to perform tasks like evaluating a situation while maintaining a low profile presents a potential model for AI that goes beyond current approaches. Maybe the efficiency might be explained by a combination of distributed processing and sophisticated coordination mechanisms. If we could somehow translate these to AI,
I think we're already seeing that with things like attention mechanisms in neural networks. These mechanisms allow the network to focus on the most relevant parts of the input, which is kind of like having a spotlight on the important features. And that allows it to process information more efficiently and make better decisions. It's all connected, isn't it? The deep learning advancements allow us to build better systems.
But attention mechanisms are still just learning statistical correlations. They're not actually understanding the meaning of the information. And that's why I think we need symbolic AI, which allows us to represent knowledge explicitly and reason about it in a logical way.
And that reasoning, I think, is often about translating between different representations. When we're trying to solve a problem, we often switch between different perspectives, different coordinate systems, different levels of abstraction. And that ability to translate is what allows us to see the problem in a new light and come up with a creative solution.
so taking it back to the paper, the fact that absolute zero can leverage self-play reinforcement learning without the need for massive data sets resonates with me. Mimicking the efficiency of learning observed in biological systems is something we can achieve, and it shows the potential.
Exactly. The zero data aspect is fascinating. It suggests that the crucial factor for AGI might be the algorithm itself, rather than simply the sheer volume of data. It potentially bypasses the need for massive datasets and paves a new path for AGI development. If the underlying principles can be scaled.
But again, how far can you scale that algorithm without it hitting a fundamental bottleneck? If it's just learning patterns, it's going to eventually run out of patterns to learn. You need to have some way of representing knowledge in a more compact and efficient way, and that's where symbolic AI comes in.
And that compact representation, I think, needs to be based on a deep understanding of space and time. We need to be able to represent objects, relationships, and events in a way that's independent of the specific coordinate system we're using. We need a truly invariant representation.
It sounds like each of us has slightly different ideas about the path forward, and that's great. It highlights the complexity of the problem and the need for diverse approaches.
Definitely. I think we're all converging on the same goal, but we have different ideas about how to get there. And that's what makes this field so exciting.
Exactly. I think it's important to explore all of these different avenues because we don't really know what's going to work in the end.
Right. It could be that the solution is a combination of all of these approaches. Maybe we need deep learning to learn low-level features, symbolic AI to represent knowledge, and a new kind of algorithm to translate between different representations.
So let's pivot to future research. Where do we see the most promising directions based on our perspectives?
For me, it's all about scaling up the absolute zero approach. I'd love to see it applied to more complex problem domains like abstract reasoning or common sense knowledge. Can it learn high-level concepts without significant pre-training? What are the scalability limitations of this approach? These are the questions that I'm most interested in.
I'd like to see more research into neuro-symbolic AI. How can we combine the strengths of neural networks and symbolic AI to create systems that are both powerful and interpretable? I think that's the key to building truly intelligent systems that we can actually understand and trust.
I want to see more focus on spatiotemporal understanding. How can we develop algorithms that can translate between different coordinate systems and reason about the world in a way that's independent of the specific representation being used? I think that's a fundamental capability that's missing from current AI systems.
From my side, I am curious to see if analyzing the agent's internal representations could reveal insights into how the brain performs learning and decision-making. And how can insights from neuroscience inform the development of more nuanced and adaptive AI models, particularly in areas like stealth and situational awareness?
And I think the most fascinating question of all is, how can we measure the stealth capability of these models in a way that transcends simple metrics like accuracy? Because that's what it's really about, right? It's not just about solving the problem, it's about solving it without being detected.
Exactly. And that requires a level of understanding that goes far beyond just pattern matching. It requires a genuine understanding of the environment, the rules, and the intentions of the other agents.
And that understanding, I think, is ultimately about building a mental model of the world that's robust and flexible enough to handle any situation. And that's the challenge that we're all working towards.
Well, this has been a really insightful discussion. It's clear that the Absolute Zero paper has sparked a lot of interesting ideas and questions. And it's also clear that we're still a long way from achieving true AGI. But I think we're making progress, and I'm excited to see what the future holds.
Absolutely. It's a fascinating field, and I'm grateful to be a part of it.
Me too. It's a privilege to be able to think about these big questions.
Definitely. It's a journey, and I'm looking forward to seeing where it takes us.
Thanks everyone for joining us on Cognitive Spirals. We hope you found this discussion stimulating. Until next time, keep exploring.